If you put two identical glasses of water into your freezer right now, one freshly boiled, one straight from the refrigerator, the boiling hot one would freeze first. Heart freezes faster. That sentence should be physically impossible. And yet, it is real. Documented by some of the greatest scientific minds in history for over 2,000 years. But here is what nobody talks about. Not a single scientist on Earth agrees on why it happens. Not one. We have theories. We have Nobel Prize winners who have weighed in. We have quantum-level computer simulations. And still, zero consensus. Later in this video, I will reveal what a team of researchers discovered in 2016. A quantum anomaly so unexpected it forced physicists to question whether our most foundational models of water chemistry are simply wrong. 2,000 years, zero answers. Why hot water freezes faster than cold water. By the end, you will understand why the most embarrassing unsolved mystery in modern science might be sitting quietly in your kitchen freezer right now. The year is 1963. A 14-year-old named Erasto Mpemba is standing in cooking class at a school in Tanzania. His assignment is to make ice cream. The instructions say to let the hot mixture cool before putting it in the freezer. But Mpemba, short on time and freezer space, puts his mixture in while still boiling hot. His froze first. His classmate's cold mixture was still liquid. He asks his teacher why. The teacher dismisses him outright. So Mpemba does what every great curious mind in history has done when dismissed. He refuses to let the question die. He tracks down a visiting physicist named Dr. Dennis Osborne from the University of Dar es Salaam and challenges him directly. Osborne could have laughed him off. Instead, he goes home, runs the experiment himself, and is stunned. It works. In 1969, they publish a paper together titled Simply Cool, and the Mpemba effect formally enters scientific literature. But here is the critical detail almost nobody knows. Erasto Mpemba did not actually discover this phenomenon. He simply happened to be the most recent person in a very, very long line of observers, because the first written record of this effect predates him by over 2,300 years. Ancient observation, modern name, and the man who first documented it will genuinely change how you see this entire mystery. Stop and think about this for a second. In 350 BC, 23 centuries before Erasto Mpemba was born, Aristotle wrote about this exact phenomenon in his treatise Meteorologica. He observed that warm water helps objects freeze more quickly and recommended that people pre-warm their water before winter storage. 350 BC. Then Francis Bacon documented the same observation in 1620. René Descartes in 1637. Robert Boyle in the same era. Generation after generation, this observation resurfaced. And generation after generation, it was shelved, because it appeared to contradict the foundational math of thermodynamics. And when an observation contradicts the textbooks, it is far easier to dismiss the observation than to question the textbooks. Observed, forgotten, rediscovered, dismissed, over and over, for 2 millennia. As Francis Bacon himself wrote, if a man will begin with certainties, he shall end in doubts. But if he will be content to begin with doubts, he shall end in certainties. If the history of this repeatedly forgotten science is already rewiring your brain, hit like and subscribe, because the next facts are even more mind-bending. Because when scientists finally ran controlled experiments in the modern era, what they discovered made the mystery significantly worse. Not better, worse. But here is where the story becomes genuinely uncomfortable for modern science. When researchers in the 20th century set up controlled experiments to finally settle the Mpemba effect, they hit a wall of contradiction. Sometimes the hot water froze faster. Sometimes it did not. Sometimes the difference was dramatic. Sometimes there was no difference at all. No pattern. In 2016, physicists Henry Burridge and Paul Linden from Cambridge University published one of the most rigorous analyses to date. Their conclusion: the effect is real, but so sensitive to experimental conditions, it almost defies standardized study. The container's size and material matters. The exact starting temperatures matter. The water's mineral content matters. Whether the lid is on or off matters. Whether the freezer shelf is metal or plastic even matters. Physicist Philip Ball reviewed decades of research on this topic and concluded the phenomenon is real, but its explanation is not settled. It may involve several contributing factors simultaneously, multiple factors simultaneously. That is not a scientific explanation. That is a scientific shrug. Real, unexplained, maddening. And when scientists tried to isolate and test each factor individually, each explanation revealed its own critical flaw. Starting with the most intuitive theory, the one that almost fooled everyone. Now here is the first theory, the one that sounds almost too logical to be wrong. When you heat water near boiling and place it in the freezer, some of that water has already evaporated, turned to steam, gone. So the hot cup now contains less water than the cold cup, and less water means less mass to freeze. Less mass freezes faster. Simple, elegant, logical wrong. Clean, intuitive, fits basic physics. For a moment, it looked like the mystery was solved, and then someone ran the actual numbers. The evaporation from a hot water sample in typical experiments reduces the mass by only 2 to 3%, not nearly enough to account for the speed advantage consistently observed. Researchers then equalized the starting masses, making sure the hot and cold samples weighed exactly the same before entering the freezer. The hot water still froze faster in many of those controlled trials. As Einstein once said, the important thing is not to stop questioning. Curiosity has its own reason for existing. The evaporation theory explains a fragment of the puzzle, but only a fragment. Something else is changing inside that water when you heat it, something invisible, something you cannot weigh on a scale. And the next theory suggests it is something your tap water has been secretly carrying your entire life without you knowing. What if I told you that the water from your kitchen tap is not pure water? It is water saturated with dissolved gases, oxygen, carbon dioxide, nitrogen, absorbed from the atmosphere and from the pipes it traveled through. These gases are completely invisible. You would never taste or smell them, but they quietly influence how water behaves at a physical level. Now here is what happens when you heat that water to near boiling. The gases flee. You can actually see it happen. Those tiny bubbles that form before water reaches a full boil are dissolved gas escaping the liquid, and water that has been degassed, stripped of its dissolved gas load through heating, does have subtly different freezing properties. Some researchers argued this was the full explanation for the Mpemba effect. Heated water, having expelled its dissolved gas content, becomes physically cleaner and freezes more efficiently, purer at the molecular level, and therefore faster to freeze. A beautiful theory, elegant, logical, except for one devastating problem. Scientists ran the experiment using water that had been pre-degassed, water with all dissolved gases already removed before any heating occurred. The Mpemba effect still appeared in many of those trials. The degassing theory is not wrong, but it cannot carry the whole explanation. Something even deeper is at work, down in the molecular architecture of water itself. And what comes next digs all the way into the bonds between atoms. Now forget everything you think you know about water for a moment, because water is one of the strangest substances in the known universe. It expands when it freezes. Almost every other substance contracts. It has an absurdly high boiling point for such a small molecule. It dissolves more substances than almost any other liquid. And behind all of this weirdness is one thing: hydrogen bonds holding everything. In 2013, researchers at Nanyang Technological University in Singapore published a controversial paper proposing something radical. When water is heated, the hydrogen bonds between its molecules stretch, storing elastic energy like compressed springs. And when that hot water begins to cool, those stretched bonds release their stored energy as they relax back. That internal energy release, they argued, could act as a hidden cooling accelerant, giving hot water a structural advantage that cold water simply does not have. As Leonardo da Vinci once observed, water is the driving force of all nature, and perhaps at the molecular level, it is also the most unpredictable force in nature. The hydrogen bond theory attracted serious scientific attention and fierce debate. But the physicist who pushed back hardest against it accidentally uncovered something even more disturbing: a crack in something that should not have any cracks at all. And the next segment, This is the one that kept me up at night. But here is what nobody tells you about what actually happens inside that cup of hot water sitting in your freezer. It does not cool as one uniform mass. The water touching the container walls drops in temperature first. The water at the center stays warmer for longer. This temperature difference between the interior and the edges creates something physical. It creates movement. Hot rises, cold sinks. Convection currents. Circular flows cycling warm water from the center out to the cold walls and back are constantly redistributing heat within the cup. Some researchers believe this is a major contributor to the Mpemba effect. Hot water, with its steep temperature gradient, generates stronger and more vigorous convection. These active currents may accelerate overall cooling by continuously bringing warm interior water into contact with the cold walls. Cold water, starting near freezing, has a sluggish internal gradient and weaker circulation. More internal movement can mean faster heat loss to the freezer walls. It sounds counterintuitive, but so does everything about this phenomenon. The convection theory has genuine experimental support, but it still cannot explain all observed cases, particularly those where convection was actively suppressed, which brings us to something that should not even be a question in modern physics, a law that has governed thermodynamics for over 300 years. A law that the Mpemba effect appears quietly and reproducibly to break. Now here is where it takes a genuinely dark turn. Newton's law of cooling is one of the cornerstones of classical physics. It states that an object's rate of heat loss is proportional to the temperature difference between the object and its surroundings. The bigger the gap, the faster the cooling, used in engineering, used in forensic science, used in medicine. 300 years of reliable prediction. Here is the problem. If Newton's law held without exception, the Mpemba effect would be mathematically impossible. Think about it. If both cups are losing heat and the cold cup already started closer to the freezing point, the cold cup should always win. The math dictates it, but the experiments contradict this, reproducibly, across different labs, different countries, different conditions. As Einstein once warned, no amount of experimentation can ever prove me right. A single experiment can prove me wrong. What researchers found when staring at this gap is a phenomenon called supercooling, where water drops below 0 Celsius without actually converting to ice. Hot and cold water appear to supercool differently. Below 0, still liquid. Hot water may bypass more of the supercooling phase entirely, but even this does not complete the picture. Because in 2016, a team ran a simulation so deep it went beneath the molecular level entirely, into quantum mechanics. And what they found there changes the entire question. Now, what I am about to tell you has been peer-reviewed, published, checked, but it still sounds impossible. In 2016, physicist Zai Zhang and colleagues at Nankai University in China ran quantum-level computational simulations of water molecules at different temperatures, not modeling how molecules interact with each other, modeling the quantum states of the atomic bonds inside individual water molecules. Inside the bond, what they found was extraordinary. The covalent OH bonds, the connections between the oxygen atom and its 2 hydrogen atoms within a single water molecule, were measurably different depending on the water's temperature history. In hot water, these bonds were shorter, stronger, and carried what the researchers described as a quantum memory of the heat the molecule had experienced. Water that was hot remembers it in its actual quantum molecular structure. If this is accurate, and the scientific debate continues fiercely, it means liquid water is not a uniform substance. Its molecular geometry is fundamentally altered by its thermal history. Every model of water chemistry that treats all liquid water as physically identical is therefore incomplete. Chemistry rewritten, quantum memory. Which discovery in this video has shaken you the most? Comment quantum memory if you made it this far. I read every single reply. And if you know someone who still believes science has answered all the basics, send them this video. Because the final piece of this story, it resolves everything and nothing. Here is the truth I promised you at the very beginning of this video. The reason no scientist can agree on why hot water freezes faster is not because they have failed to look hard enough. It is because the Mpemba effect almost certainly has multiple simultaneous causes, and which one dominates depends entirely on the specific conditions of each individual experiment. Many causes, one effect: evaporation, dissolved gas loss, convection dynamics, hydrogen bond elasticity, supercooling thresholds, quantum memory in covalent bonds. All of these mechanisms are likely real, all of them likely contribute. And depending on the container material, the water source, the temperature differential, and the freezer environment, a different mechanism steps forward and dominates. This is why the same experiment yields contradictory results in different labs. 2,000 years of observation, and the cause is still not singular. As Richard Feynman once said, the first principle is that you must not fool yourself, and you are the easiest person to fool. Science's most honest and most powerful answer is sometimes simply, we do not fully know yet. And sometimes the deepest mysteries are not hiding in distant galaxies or billion-dollar particle accelerators. Sometimes the greatest unsolved mystery is in a glass of water on your kitchen counter, waiting for 2,000 years, for someone curious enough to keep asking why. From a teenage boy's ice cream in a Tanzanian cooking class to quantum-level simulations of atomic bonds. From Aristotle's scrolls in 350 BC to the laboratories of Cambridge and Nankai University in 2016. 2,000 years, no consensus. The Mpemba effect is not just a physics curiosity. It is a mirror held up to the limits of human knowledge, a reminder that even in the most ordinary things, a glass of water, a kitchen freezer, a cup of boiling tea, reality keeps harboring secrets we have not yet fully deciphered. And that is not a failure of science. That is science working exactly as it should. As Carl Sagan once wrote, somewhere, something incredible is waiting to be known. The Mpemba effect is that incredible thing, hiding in plain sight, in your freezer, right now. Next time you boil a kettle, pause, and remember what the world still does not understand. Science is not a finished building. It is a construction site, and some of the most beautiful questions are the ones left beautifully open. If you made it this far, prove it. Comment Mpemba below. Join the few who actually know this story. The truth is stranger than anything you could make up.